Hello, this video is about some exciting joint work with Anindya and Rocco Servedio, and it's about quantitative correlation inequalities. So let me start off by telling you what a correlation inequality is. You've got some probability space, and you're interested in some class of functions over this probability space. And a correlation inequality simply tells you that any two functions belonging to this family are non-negatively correlated. And these are very fundamental, very useful tools in combinatorics and statistical physics. If you were to grab your copy of Alon and Spencer, for example, you'd find an entire chapter devoted to these sorts of statements. Perhaps the simplest correlation inequality is the Harris-Kleitman inequality, which says that any two monotone Boolean functions on the n-dimensional hypercube are non-negatively correlated. So the n-dimensional hypercube is just a collection of 0, 1 strings of length n, and a function is said to be monotone if flipping an input bit from 0 to 1 cannot cause the value of the function to decrease. And this inequality is not too hard to prove. In fact, we'll essentially prove it in a few minutes. It's also been known for over 50 years. It was proved in 1966. A more recent correlation inequality is Royen's inequality, which was proved in 2014. It concerns symmetric convex sets of a Gaussian space, where by Gaussian space, I just mean Rn endowed with the standard Gaussian distribution. And we say a set is symmetric if it's symmetric about the origin. In other words, if a point x is in the set, then the point minus x obtained by flipping the sign of each of x's coordinates is also in the set. And Royen's inequality says that if you've got two symmetric convex sets, then the indicator functions of these sets are going to be non-negatively correlated with respect to the standard Gaussian distribution. Another way of stating Royen's inequality is as follows. It says that the Gaussian measure of the intersection of two symmetric convex sets is at least the product of the Gaussian measures of the sets themselves. And there's many other correlation inequalities for different interesting classes of functions and a bunch of different domains. But in this video, we'll just be focusing on the two examples we just saw, the Harris-Kleitman inequality and Royen's inequality. One thing to note about both these statements, in fact, all the inequalities in the previous slide, is that they're all qualitative in nature. All they say is that this correlation between any two functions belonging to some family is non-negative. And so it's natural to hope for a better lower bound on this correlation, perhaps in terms of some property of the functions that we are considering. And with this in mind, let's actually revisit the Harris-Kleitman lemma and try to see what a quantitative version of it would look like. So here's Harris-Kleitman. You've got these two monotone Boolean functions on the n-dimensional hypercube. And a natural thing to do is to define restrictions of these functions to the n-1 dimensional hypercube as follows. So given the function f, you can define this new function f0 obtained from f by fixing the last bit of f to be 0. And you can similarly define g0 by fixing the last bit of g to be 0. And you can define f1 and g1 by fixing the last bits of f and g to be 1 respectively. And now that you've got these restricted functions, you can express this correlation between f and g in terms of these restricted functions. To obtain this expression, this is not too hard to see, and feel free to pause the video and verify this. But each of the expressions on the right-hand side is a pretty interesting quantity. In particular, the first one is nothing but half the correlation between the restricted functions f0 and g0. The second one is nothing but half the correlation between the restricted functions f1 and g1. And so if you were trying to prove Harris-Kleitman by inducting on the dimension of the hypercube n, then since these restricted functions are n-1 dimensional, they're going to be non-negative by the inductive hypothesis. And this third quantity, it's an interesting looking quantity which some of you might have seen before. Let's actually just focus on the first term in this product. And feel free to take a moment to verify this. If the function f is monotone, then this highlighted quantity is precisely the probability that when you choose a point x uniformly at random from the Boolean hypercube, the value of f at that point differs from the value of f at the point obtained by flipping the last bit of the original point x. And this is a well-studied notion. So let me say a little bit about this quantity in slightly more generality. So given a Boolean function on the n-dimensional hypercube, you can define the influence of any of its n coordinates as this probability of this probability that when you choose a point uniformly at random from the hypercube, the value of f at that point differs from the value of f at the point obtained by flipping the coordinate you're interested in. And this probability is the influence of that coordinate. It captures in some sense how much the function f depends on that particular coordinate. And there's been a long line of very interesting, very exciting work built around this notion of influence. Returning to Harris-Kleitman, it's easy to see that the Harris-Kleitman inequality is tight, or in other words, this correlation between two monotone Boolean functions is zero if and only if for each coordinate, the influence of that coordinate on either f or on g is zero. Or in other words, at least one of f or g is independent of that coordinate. And so it's natural to hope for a better lower bound in the Harris-Kleitman inequality in terms of the sum of the products of the influences of the two functions. And what this quantity is capturing is, in some sense, how much the functions f and g depend simultaneously on the same set of coordinates. And such a lower bound was obtained by Talagrand in 1996. Talagrand showed that if you've got two monotone Boolean functions on the n-dimensional hypercube, then you can lower bound the correlation between these two functions in terms of this function psi of the sum of the products of the influences of the two functions. And this function psi of x is defined to be x over log of e over x. And this logarithmic factor turns out to be necessary, so Talagrand's inequality is tight. Talagrand's proof is not so easy, and the key technical lemma is this decouple level 2 inequality, for those who are familiar with Boolean function analysis. And this key technical lemma has many interesting applications elsewhere in combinatorics and Boolean function analysis. So to summarize the situation so far, we've got these two really nice qualitative statements for monotone Boolean functions over the n-dimensional hypercube and for symmetric convex sets of a Gaussian space. And Talagrand comes along and robustifies the expression on the left to obtain this really interesting looking correlation inequality. And it's natural to hope for a robust version of Royen's inequality or a Talagrand analog for symmetric convex sets of a Gaussian space. And that's precisely what we obtain in this work. We show that the correlation between any two symmetric convex sets can be lower bounded by this function phi of the sum of the influences of these convex sets. So this inequality looks a lot like Talagrand's inequality, but a key difference is this function phi, which has an additional logarithmic factor in the denominator. And I also haven't told you what this notion of influence for a symmetric convex set of a Gaussian space is. So let me put up our results in slightly larger font. This is the main theorem that we'll be after for the rest of this video. And along the way, I will actually tell you what this new notion of influence is for symmetric convex sets actually is. And I just want to emphasize one thing that I will say more about later, but the strategy we use to prove this theorem generalizes very easily to a bunch of different domains. In particular, if you want to recover Talagrand's result of a 0, 1 to the n, you can essentially follow the strategy we'll be using to prove this theorem and obtain a quantitative correlation inequality, which looks like Talagrand's inequality, but has this additional logarithmic factor, or in other words, has this phi function as opposed to Talagrand's c function. Let me sketch the proof strategy we'll be following very, very briefly. So we've got these two symmetric convex sets, K and L, and we're interested in the correlation between these two sets. And what we're going to do is we're going to be interpolating between each of the two terms in this correlation quantity. And there's a natural way of doing this by starting with the expectation of K times L and adding noise to the inputs of one of these two indicator functions, say to K. And eventually you add enough noise that this noisy version of K becomes independent of L. And so this expectation splits into the expectation of K times the expectation of L. And we'll be doing this interpolation using the Ornstein-Uhlenbeck noise operator. Once we've got this interpolation, we're going to be expressing it as a power series. And we'll be doing this using the Hermite Basis. And we'll require a complex analytic lemma, which I won't be proving in this video. But essentially, the lemma says that the value of this power series is going to be large at some point along the interpolation. And finally, because of the monotonicity of this interpolation, we'll be able to conclude that the correlation between these two sets is large. And this monotonicity turns out to be a consequence of Royen's proof of the Gaussian correlation inequality itself. And so the rest of this video will look like this. We're going to start off by doing some harmonic analysis of a Gaussian space. I'll define this Hermite basis and the noise operator, after which we'll briefly touch upon Royen's proof, and then we'll put all these ingredients together to get the quantitative Gaussian correlation inequality that I showed you a few slides ago. And finally, I'll say a little bit about this new notion of influences for symmetric convex sets, and I'll tell you how the strategy generalizes to other domains. So let's get started. We're going to be interested in the vector space of square integrable functions of a Gaussian space, L2, and we're going to be thinking of it as an inner product space where the inner product between two functions f and g is simply the expectation of f times g. And it's a standard fact that the Hermite polynomials, the univariate Hermite polynomials, form a complete orthonormal basis for square integrable functions of a one-dimensional Gaussian space. The exact expressions for these polynomials don't really matter. All that really matters for us is that they're orthonormal. So we've got this nice orthonormal basis for functions of a one-dimensional Gaussian space. And a natural thing to do is to tensorize them to obtain a basis for functions of an n-dimensional Gaussian space. And so a little bit of notation, given an n-tuple of natural numbers alpha, we're going to define this multivariate Hermite polynomial, h sub alpha, where h sub alpha of x is defined to be the product of the univariate Hermite polynomials, h sub alpha I of xi. And it's a standard fact that the collection of these multivariate Hermite polynomials is a complete orthonormal basis for square integrable functions of an n-dimensional Gaussian space. In other words, this lets you write a function in L2 as a combination of these multivariate Hermite polynomials. And this combination, this expression is called the Hermite expansion of this function f. In particular, these f tilde alphas, which are real numbers, these coefficients are called the Hermite coefficients. And the collection of these coefficients is the Hermite spectrum. An easy consequence of orthonormality of the Hermite basis is that given two functions f and g with these Hermite expansions, the inner product of f and g, which we define to be the expectation of f times g, is nothing but the sum of the products of the corresponding Hermite coefficients of f and g. This is pretty much all the harmonic analysis we'll need. So let's actually move on to the noise operator. So there's the Ornstein-Uhlenbeck noise operator is analogous to the Bonami-Beckner noise operator over the Boolean hypercube. And it's defined as follows. Given a function f, you define the new function u rho of f as follows. U rho f of x is defined to be the expectation of f of rho x plus square root 1 minus rho squared g, where the expectation is taken with respect to g. This number rho ranges between 0 and 1, and we're going to be thinking of it as a noise rate, where when rho is large, we are adding very little noise to the function. And when rho is small, you've added lots of noise to this new function u rho f. And essentially, this function is a constant, forgets about the input. More concretely, when rho is set to 1, it's easy to see that u rho f of x is just f of x. And when rho is 0, u rho f of x is just the constant function, which is the expectation of f. So as you're decreasing rho from 1 to 0, you're adding more noise to the function. And this Ornstein-Uhlenbeck noise operator interacts really, really nicely with the Hermite basis. And before I show you how it does, how does that, we'll need some notation. Given an n-tuple of natural numbers, alpha, we're going to be defining the degree or the level of alpha, and also by use of notation, the degree or level of a Fourier Hermite coefficient f tilde alpha as the sum of the entries of alpha, and we'll be denoting it by this absolute value of alpha. And it's a really awesome fact that the Hermite basis is diagonalized by the Ornstein-Uhlenbeck operator. In other words, if you've got a function f with this Hermite expansion, the Hermite expansion of u rho f looks a lot like the Hermite expansion of f, but with all the Hermite coefficients scaled by rho to the degree of the Hermite coefficient. And so just a quick summary of this section. Given a function f in L2, you can write its Hermite expansion. You've got Parseval's formula, which is an easy consequence of orthonormality of the Hermite basis. And you've got this really nice noise operator, which interacts really nicely with the Hermite basis. And a good reference for all of this is chapter 11 of Ryan O'Donnell's analysis of Boolean functions. So let's move on to Royen's proof. In case you've forgotten, what Royen showed is that any two symmetric convex sets are non-negatively correlated under the Gaussian distribution. And what we're going to do is we're going to be expressing each of these terms in this correlation, the expectation of k times L and the expectation of k times the expectation of L, in terms of an inner product of a noisy version of k and L at different noise rates. More concretely, it's easy to see that the expectation of k times L is nothing but the inner product of u rho k and L when rho is set to 1. And the expectation of k times the expectation of L is the inner product between u rho k and L when rho is set to 0. Or in other words, the noise is very high. And so Royen's inequality says that this inner product at noise rate 1 is greater than the inner product at noise rate 0. So let's actually see how Royen proves this. So here's Royen, and here's what he wants to prove. He wants to show that this inner product at 0 is going to be less than or equal to the value of the inner product at 1. And Royen's insight was to look at not just these two points of this, the value of this inner product at these 2 points, but actually at the value of this inner product at all noise rates between these two noise rates. So you end up with a curve that might look something like this. And Royen doesn't seem too pleased with this curve because it's sort of a wild curve. It goes up and then down and then all the way back up again. And Royen realizes that this actually cannot happen. Royen shows that the curve's got to look something like this. More formally, what Royen shows is that this inner product between u rho k and L is increasing in this noise parameter rho. So once you've got this monotonicity of this inner product, this qualitative Gaussian correlation inequality is immediate. It's an easy consequence, and this monotonicity will be crucial for us as well when we prove the Talagrand analog for symmetric convex sets of Gaussian space. So let's move on to proving this robust Gaussian correlation inequality. So we have these two symmetric convex sets, and we want a quantitative lower bound on the correlation between them, which we have an expression for in terms of the difference of this inner product at 2 different noise rates. Since we defined the Hermite basis, let's actually write down this inner product in terms of the Hermite coefficients of the functions k and L. So the Hermite expansion of u rho k is given by this expression, and the Hermite expansion of L is given by some expression on the right. And because of Parseval's formula, it follows that this inner product is the sum of the products of the Hermite coefficients, the corresponding Hermite coefficients of k and L, multiplied by rho to the power, rho raised to the degree of the Hermite coefficients. And so let's subtract the inner product at noise rate 0 to obtain this expression, which is the sum of the products of the Hermite coefficients scaled by rho to the degree of the Hermite coefficients, where the sum is taken over Hermite coefficients of degree strictly greater than 0. And just to reparameterize this expression, we can write it in terms of a power series as follows. This is a power series in rho whose coefficients, AIs, are given by the expression on the slide. In particular, AI is defined to be the product of the Hermite coefficients of k and L of degree I. And it's easy to see using the Cauchy-Schwarz inequality and Parseval's inequality that the sum of the absolute values of these coefficients is at most 1. And because k and L are symmetric, the indicator functions of k and L are even functions. And it follows that the Hermite coefficients of k and L of odd degree are going to be 0. And this is because the multivariate Hermite polynomial 8 sub alpha is even if the degree of alpha is even, and it's odd if the degree of alpha is odd. So let's incorporate these two facts into this power series. The symmetry will kill off all the indices a sub I when I is odd. So you can just write this in terms of these even indices. And we have this additional constraint that the sum of the absolute values of these coefficients is at most 1. And we're going to actually pull out this A2 and write this difference as A2 times this new power series P of t. And there's some nice properties about this power series P of t. Its constant term is 0. In other words, P of 0 is 0. The linear coefficient is 1. And the sum of the absolute values of the coefficients is bounded by 1 over A2. This is a consequence of the fact that sum of the absolute values of the AIs is bounded by 1. And this new variable t is nothing but rho squared. So we've just reparameterized this to make things slightly easier for us. And the question we're interested in now is how large the largest value of P of t is as t ranges over the unit interval. Once we've got a lower bound on the supremum, it's easy to get a lower bound on the correlation because of Royen's proof. So this was a bit of a spoiler, and it'll become clear in a few moments. So we've got this power series, and we want to lower bound the supremum of this power series. And it actually turns out to be easier to analyze this question in slightly more generality. In particular, instead of restricting the coefficients of these power series to be real numbers, we're going to be thinking of complex power series. So you've got some power series, P of t, with complex coefficients, such that the constant term is 0. In other words, P of 0 is 0. And the coefficient of the linear term is 1. And you're interested in the modulus of P of t as t ranges over 0 to 1. In particular, you're interested in the supremum of this modulus of the unit interval. And you've got this additional constraint that the sum of the sum of the moduluses moduli of the coefficients of this power series P is bounded by m, where m is some number. More formally, you've got P of t given by this complex power series with C1 equal to 1. And the sum of these, the magnitudes of these coefficients is bounded by m, where m is bounded, m is at least 3 over 2. The exact value, 3 over 2, doesn't really matter too much. All that really matters is that it's bounded above 1. And we've been asking this question. We asked this question: how large must the supremum of the modulus of this power series be of the unit interval? And our answer to this question is the following: we show that this quantity is at least on the order of 1 over log squared m. And the proof of this this lemma uses the Hadamard 3 circles theorem. I'm not going to be going over the proof in this video. And I also want to say that this bound is tight. We have a construction using Chebyshev polynomials, which matches this bound. So returning to the proof of the Talagrand analog for symmetric convex sets, we had this expression for the difference in the inner product at two different noise rates in terms of A2 times PT, where PT was this power series. And we wanted to lower bound the supremum of this power series over the unit interval. And because of the previous complex analytic lemma that I just showed you, it follows that the supremum of P of t as t ranges over 0 to 1 is at least on the order of 1 over log squared 1 over A2. So just to verify that this power series P meets the conditions on the previous slide, its constant term is 0, its linear coefficient is 1, and the sum of the absolute values of the coefficients of P of t is bounded by 1 over A2. And A2 is non-negative. This is not too hard to see because of Royen's proof. So we've got a lower bound on the supremum of this difference of the inner product because of the supremum, because of the lower bound on the supremum of P of t as t ranged over the unit interval. And because of Royen's proof, we know that this inner product is increasing in rho. In other words, the difference in the inner product of U rho k and L at noise rate 1 and at noise rate 0 is at least on the order of A2 over log squared 1 over a2. In other words, it's equal to some constant times this function phi that we showed up that showed up earlier, and the input to this function phi is a2. And just to be completely clear, phi of x is just x over log squared 1 over x. And this is a quantitative version of Royen's inequality, but I promised you a quantitative version which had this notion of influences. So let's maybe look at this quantity a2 a bit more closely. So given two symmetric convex sets, a2 is defined to be the product of the Hermite coefficients of K and L of degree 2. The product of the corresponding Hermite coefficients of K and L. And let's look at how let's look at these Hermite coefficients of degree 2. So just some notation. Let EI denote the standard basis vector in n-dimensional space, where the ith entry is 1 and all the other entries are 0. And if the degree of an n-tuple of natural numbers alpha is 2, then it's either got two non-zero entries which are both 1s, or it's got a single non-zero entry which is 2 and everything else is 0. And it's actually not super hard to see that if you've got a symmetric convex set K, then there's some suitable rotation of this set, rotation of the space, such that all these mixed Hermite coefficients die out. In other words, these K tilde alphas are going to be 0 whenever alpha is a degree 2 Hermite coefficient of the form EI plus EJ, or in other words, alpha has two non-zero entries which are both 1s. And now that you've performed this rotation, you can actually write A2 as the sum of the products of these degree 2 Hermite coefficients, where the coefficients of the form are of the form 2 EI for some I ranging between 0 and 1. And inspired by the resemblance with Talagrand's inequality, it turns out to be it's a natural thing to define these Hermite coefficients, these degree 2 Hermite coefficients, as the influences. We're going to be negating them, and the reason for this will become clear on the next slide. So given a symmetric convex set K, we're going to define the influence in the ith direction as this negated Hermite coefficient, where the Hermite coefficient is a degree 2 coefficient with one with one non-zero entry, namely a 2 at the ith coordinate and a 0 everywhere else. And so this quantity A2 is nothing but the sum of the products of the corresponding influences of K and L. And let me actually say why why it's actually not an insane thing to think about these influences, these negated degree 2 Hermite coefficients as influences. In particular, we show that the influence of a symmetric convex set K is non-negative with equality if and only if K is entirely independent of the ith coordinate. And so this is in some sense, this resembles what the influences for Boolean functions in the n-dimensional hypercube behave like. And many other interesting analogies seem to hold, and we've been exploring this notion further. So here's the quantitative Gaussian correlation inequality that we prove. It says that any two symmetric convex sets, the correlation of any two symmetric convex sets can be lower bounded by this function phi of the sum of the products of the influences, where this function phi of x is defined to be x over log squared 1 over x. Let me finally say a little bit about how this strategy generalizes to other domains. So let's look at what we really did. We had some probability space, Rn, and that with the Gaussian distribution. And we were interested in this correlation quantity. And we interpolated between this expectation of f times g and expectation of f times the expectation of g. And in the setting of symmetric convex sets of a Gaussian space, we interpolated using this Ornstein-Uhlenbeck noise operator. But a more general way of doing this is to define an appropriate Markov semigroup on this probability space. We then expressed it as a power series using the Hermite basis. And more generally, we can express it as a power series using the eigenfunctions of, of an appropriately defined Markov semigroup. And finally, we use the monotonicity of this interpolation. And this is often available in the form of off-the-shelf results because, as was in the case with the Gaussian correlation inequality, many qualitative correlation inequalities have been proved by proving the monotonicity of this interpolation. And so this lets us obtain Talagrand analogs over a bunch of different domains. And one thing which I want to emphasize is that there doesn't seem to be a canonical choice of Markov semigroup to put on some of these domains. For example, over the solid cube, 0, 1 to the n, you could either put the ultraspherical Markov semigroup, which diagonalizes the Legendre polynomials, or you could put the reflected heat semigroup, which diagonalizes the cosine basis. And for each choice of this Markov semigroup, you get a seemingly different quantitative correlation inequality. So to summarize, we have this approach to getting quantitative correlation inequalities from qualitative ones. And the two main ingredients going into this approach are this idea to interpolate using noise operators, which people have done before. And we have this complex analytic lemma, which may be of independent interest, which bounds the supremum norm of complex power series of bounded length. And we also have this new notion of influence for symmetric convex sets of a Gaussian space, which is pretty exciting and lots of interesting analogies with some of the results from Boolean function and analysis seem to hold. If you made it this far, thanks for watching.